fluid dynamics, and flow measurements. Different kinds of forces acting on a fluid particle. To analyze fluid flow comprehensively, the fundamental dynamics forces acting on an individual fluid element must be identified. These core forces include pressure force arise due to arise due to special gradient of pressure within the fluid domain, gravity force, body force representing the gravitational pull acting on the fluid element mass, viscous force, shear force originating from the internal fluid friction and viscosity effects. If all the three primary forces, pressure, gravity, viscous force, are comprehensively taken into account during different dynamic modeling, the system equation obtained is known as Navier-Stokes equations. Euler's equation. Euler equation represents the dynamic momentum conservation equation evaluated specifying along a streamline for an idealized fluid environment. Core assumptions: the flow is two-dimensional, fluid is completely inviscid, no viscous friction effects are considered, F B is equal to 0. The flow field state is steady over time. The mathematical differential form of Euler's equation along a streamline path is formulated as dp by rho plus g dz plus vdp is equal to 0. Bernoulli equation. Bernoulli's equation represents a crucial conservation of mechanical energy principle along a continuous path directly derived by integrating the differential Euler equation under precise constraint. Assumption in Bernoulli equation: the fluid is ideal, zero viscosity. The flow state is steady. The medium is continuous. The fluid is completely incompressible. Rho remains constant. The flow behavior is non-viscous. The flow field is irrotational. The relationship is strictly applicable along a single designated streamline. P by W plus Z plus V square by 2 is equal to C. P by W pressure head, Z gravitational head, atom head, P by W plus Z piezometric head, V square by 2G kinetic energy head, C total energy constant along a streamline. Venturimeter. A venturimeter is a standard line integrated differential device utilizing a localized internal throat convergence to measure the volumetric rate of flow with closed pipe system. General property and geometric limits. Inlet and main pipe diameter denoted as D1, throat narrowing section diameter denoted as D2, proportions by D2 is equal to one third or one half of D1. Angle of convergence forms at 22 degree to graceful step or fully step of velocity. Angle of divergence kept narrow at 6 degree to 7 degree. It must exceed 7 degree to effectively prevent boundary separation and closed all eddies. Fluid mechanics discharge formulations. Q ideal is equal to A1 A2 root 2 GS by A1 square minus A2 square root over parameter definition, where H defines the net geometric head difference. H is equal to P1 minus P2 by W is equal to V2 square minus P1 square by 2G, assuming gravitational atom head difference 0. Manometer equation for heavier fluid. When computing differential pressure using an integrated U-tube manometer containing a heavier fluid, Hx to Sm by S minus 1, X manometric liquid reflection height, Sm relative density specific gravity of the heavy manometric fluid, S relative density of the system flowing fluid. Fluid dynamics, discharge consideration, actual discharge consideration, Q actual is equal to CdP into Q ideal. For standard venturimeter, the efficient streamlining delivers a high coefficient of discharge CdP is equal to 0.94 to 0.98. The mathematical representation of coefficient of discharge in terms of head loss in the convergence section is defined by CdP is equal to H minus HL by H root over orifice meter. An orifice meter is an alternative primary device working on identical differential throttling principles. It consists of a thin flat plate with a sharp edge circular hole positioned concentrically inside the pipe wall. Although significantly cheaper to produce and install than a ventimeter, it causes severe unguided fluid turbulence leading to high net energy loss. Discharge formulation QCD A1 A naught by root over of A1 square minus A naught square whole 2GH. A1 pi by 4 D square cross sectional area of the main pipeline. A naught pi by 4 D naught square cross sectional area of the orifice aperture. Primary application standard closed conduit fluid rate of flow measurement, discharge coefficient constant CT 0.64 to 0.76, notably lower due to turbulent separation downstream. Fundamental interrelation CC by CB, here CC coefficient of contraction, CD coefficient of discharge, and CB coefficient of velocity. Peter tube. A Peter tube acts as a dynamic structural tool operating on the core physical principles of transforming localized stream kinetic head into static pressure head. The special point where moving fluid velocity is brought locally to absolute rest is explicitly identified as the stagnation point. Core function. A Peter tube acts as a dynamic structural tool of stream kinetic head into static pressure head. Stagnation point definitions V equal to 0. The Peter tube acts where stagnation point increase static pressure head. Example applications air speed indicators. Example of application forms air speed indicator and state stress terms. Theoretical and actual velocity formulations. V theoretical root 2 g h 2 j whole ps minus p naught by rho 0 root over v CV theoretical CV coefficient of velocity typically calibrated near 0.98 ps by rho j ps by rho j. Stagnation pressure P naught by rho j. Static system pressure head. Operation concept. The operational velocity head is directly tracked via the fluid column height by variation existing between the inner pitot tube probe and an exterior static piezometer. Because the internal probe registers aggregate energy effects, it is often termed as total head tube. Application in closed conduit infrastructure. So when installed within pressurized pipeline channel, coupled alongside a manometric records V1 root 2 GS where HX SMIS minus 1. Technical definition of hydraulic coefficients. Hydraulic performance validation rely on three specific dimensionless ratio. Coefficient of contraction CC, area of jet at vena contractor by area for temperature. Coefficient of velocity, actual stream velocity by theoretical stream velocity. Coefficient of discharge is actual volumetric discharge by theoretical volumetric discharge. Comprehensive summary of flow measuring device. The flow table represents the structural summary of standard flow measuring instruments and their exact industrial and resource applications. Inchrometer, volumetry rate of flow discharge in pipeline with low energy loss. Flow nozzles, volumetric rate of flow discharge inside high velocity fluid paths. Orifice meter, the volumetric rate of flow where economic layout is prioritized. Band meter, volumetric rate of flow utilizing centrifugal pressures differences across standard elbow. Rotameter, real-time visual volumetric flow rate tracking utilizing a variable area plotting cone. Peter tube point specific fluid flow velocity based on stagnation pressure conversions. Instantaneous hot wire anemometers, instantaneous air and gas localized velocity fluctuation. Current meters localized stream velocity evaluations across large open channels.